students, in previous video we have discussed what is a vector space, and we have also seen one example based on vector space. Okay, in your textbook there are some small examples, so study that examples. In this lecture we see one theorem. Let V be a vector space. Let V be a vector space. Let U belongs to V, K belongs to R. Then first is 0 into U is equals to 0. B, K into 0 is equals to 0. C, minus 1 into U is equals to minus U. And D is, if K into U is equals to 0, then either K is equals to 0 or U is equals to 0. Okay, proof of this theorem is very simple. This is homework to you. What is theorem? Let V be a vector space. Let U belongs to V. K is any real number. Then what happened? 0 into U is equals to 0. B is K into 0 is equals to 0. C, minus 1 into U is equals to minus 1. And D is, if K into U is equals to 0, then either K is equals to 0 or U is equals to 0. Let us take definition. Let Rn denote the set of all ordered n tuples. Set of all ordered n tuples of real numbers. Two vectors V is equals to V1 comma V2 and so on up to Vn, and W is equals to W1 comma W2 and so on up to Wn, are called equal vectors if these two vectors are equal. If first component of V is equals to first component of W, means V1 is equals to W1, V2 is equals to W2 and so on up to Vn is equals to Wn. Okay, the sum, next is the sum V plus W is defined as component wise addition. Component wise addition is U plus W is equals to V1 plus W1, means add first component of V and first component of W. Second element is second component of V plus second component of W, V2 plus W2 and so on up to Vn plus Wn. Okay, the scalar multiplication for any K belongs to R is defined as follows. is defined as follows, means k into v is equals to k into v1, v2 and so on up to vn is nothing but k into v1, k into v2 and so on up to k into vn. These operations are called standard operations on these operations are called standard operations on Rn. These operations are called standard operations on Rn. Standard operations on Rn. Okay. These operations means what? Addition and this scalar multiplication are called standard operations on Rn. Now we will see some examples of set which is not a vector space. Okay. Which is not a vector space. First example is, let V is equals to set matrix vector xy such that this x is greater than or equal to 0, y is greater than or equal to 0. Means x is either 0 or greater than 0. That is V is a set of vectors. V is a set of vectors from first quadrant only is not a vector space. Is not a vector space. Okay. Solution. See here, if you take u comma v belongs to v, then what happened? U plus v is obviously belongs to v. Okay. Means what? If you take u is equals to x1 y1 and v is equals to suppose x2 y2, and if you take addition of these two vectors, this is x1 plus x2 and y1 plus y2. This addition is belongs to v. Why? Because this x1 and x2 are both greater than or equal to 0. That's why their addition must be greater than or equal to 0. Similarly, y1 plus y2 is also greater than or equal to 0. That's why u plus v belongs to capital V. Okay. However, if c is equals to -1, then for any u belongs to v, c into u does not belongs to v. Why? As if you take here c is equals to -1 into xy is nothing but vector -x minus y. But this vector -x minus y does not belongs to this v, because this x and y are most greater than or equal to 0. Therefore, This is does not belongs to V. V is any set V is not vector space means what? That set must fail any set V is not vector space means what? That set must fail to satisfy the any one of the axioms of vector space. See here, this set fails to satisfy the axiom C into U belongs to V. That's why this set is not a vector space. Okay, I hope all of you understand this concept. Means we have to find one axiom that not satisfy the which is not satisfy the set S, any set. Okay, let us take one more example. Second, suppose S is a set of all polynomials of degree 2 such that sum of their coefficient is 3. Sum of their coefficient is 3. Show that S is not a vector space. S is not a vector space. Show that S is not a vector space. Okay. Solution. Means here we have to find a axiom which is not satisfied by F. Okay. Let S is what? Set of all polynomials of degree 2 such that sum of their coefficient is 3. Means what? ax square plus bx plus c. S is a set of all polynomials of degree 2 such that sum of their coefficient means a plus b plus c is equals to 3. A, B, C, R belongs to R. This S is a noun. S is not a vector space. Why this is? Because take one particular case. For P of x is equals to x square plus 2x, and if we take Q of x is equals to 2x square plus 1. See here, this is a polynomial of degree 2, also this is a polynomial of degree 2. Sum of their coefficients is 2 plus 1 is 3. Also here sum of their coefficient is 3. We observe that P of x comma Q of x belongs to S. But if you take their addition, P of x plus Q of x is equals to what? 3x square plus 2x plus 1, which does not belong to S, because this is S is a set of all polynomials of degree 2 such that sum of their coefficient is 3. But here sum of coefficient is 3 plus 2 plus 1 is equals to 6. That's why this sum does not belongs to hence vector addition is not closed in S. Therefore, S is not a vector space. Okay. Let us take next definition. Subspace. Its definition is, actually subspace is nothing but any subset of a vector space is a subspace when it is a vector space itself. Definition 1. Let V be a vector space. Let V be a vector space and W is a subset of V. Okay. Then W is a subspace of V. W is a subspace of V if W is itself a vector space with respect to the operations of vector addition and operations of vector addition and scalar multiplication on V. Scalar multiplication on V. Okay. Means what? Any subset of a vector space is a subspace if it is itself a vector space. Okay. Let's take definition 2. A subset W of vector space V of a vector space V that satisfies the following three properties. Okay. First one is the zero vector of V is in W. Means what? 0 belongs to W. A subset B, W is closed under vector addition. W is closed under vector addition. That is, for U comma V belongs to W implies U plus V belongs to W. C. W is closed under scalar multiplication. W is closed under scalar multiplication. W is closed under scalar multiplication. That is, for C belongs to R and U belongs to V, that implies C into U belongs to W, is known as subspace of V. Means any subset W of V, it satisfies these three properties, then we say that W is subspace of V. Okay. Now here let us take one remark, or we can say note. By combining say this is suppose 1, combining B and C from the definition of subspace, from the definition of subspace, we state the following result. A subset W is a subspace of V if and only if first is W contains the zero vector. W contains a zero vector. Okay. And B is, for all C comma D belongs to R, U comma V belongs to W, Cu plus DV belongs to W. Means we combine this B and C. So this will become Cu plus DV belongs to W. Okay. Let us take next remark. That remark is second. W is non-empty subset of V. W is non-empty subset of V. As why this is W is non-empty subset of V? As it contains a zero element of V. At least zero element of V. That's why W is non-empty subset of V. Third is, every subspace is a vector space. Third is, every subspace is a vector space, and every vector space is a subspace. Every vector space is a subspace of itself. Every subspace is a vector space, and every vector space is a subspace of itself. Okay, let us take some examples on subspace. Example number 1. Let W is equals to singleton 0, where 0 is the 0 vector of V, then W is a subspace of V. Then W is a subspace of V. It is called a zero subspace. It is called a zero subspace of V. Obviously, W is equals to singleton 0 is a subspace of V, and this subspace is called zero subspace of V. Example number 2. Suppose V is equals to R2. W is a line passing through the origin. W is a line passing through the origin. W is a line passing through the origin. Origin means order pair 0, 0. Then W is a subspace of R2. Then W is a subspace of R2. Okay. Let us take solution of this problem. Here W is a line passing through the origin. Means what? W is the set of all order pair xy such that y is equals to x. X and y belongs to R. Okay. We have to prove that this W is a subspace of R2. First, clearly order pair 0, 0 is belongs to W. Obviously. Now we have to prove property B and C. Here W is equals to order pair xy such that y is equals to x. So here, okay, here we can write W is equals to order pair xx such that x is belongs to R, because our set is order pair xy such that y is equals to x. Okay, here we have just substitute y is equals to x. Now clearly 0 vector 0, 0 is belongs to R, because W is of the form x, x means x coordinate and y coordinate are same, and in origin this x coordinate and y coordinate is 0, 0. That's why this order pair 0, 0 is belongs to W. Now we have to prove W is a closed under vector addition. If you take U is equals to order pair x1, x1, and V is equals to order pair x2, x2, then what happened? Suppose U plus V is equals to x1 plus x2, x1 plus x2, means x and y coordinate are same. That's why this is belongs to W. This is therefore W is closed under. Therefore W is closed under vector addition. Therefore W is closed under vector addition. Okay. Suppose this is A property, this is B. Now we have to prove W is closed under scalar multiplication. So that's for this C into U. C into U is suppose x1, order pair x1, x1, which is equals to order pair C into x1, C into x1. Again here x and y coordinates are same, that's why this C into U is belongs to W. Therefore W is closed under scalar multiplication. Scalar multiplication. Therefore W is a subspace of V. Therefore W is a subspace of V. Okay. Students, let us take one example for homework. That example is, suppose V is equals to m by n, a set of matrices of order m by n with real entries. We define W is equals to set matrix A, B, 0, D such that A, B, D belongs to R. Show that W is a subspace of W is a subspace of V. Show that W is a subspace of V. Okay students, we will stop here. Thank you.